Justice, what's going on, my friend?
Not much. Oh, is it just me right now?
Just you. I was a minute early today. I just could not wait another second to see you guys.
Ah, I see. I gotta go grab my notebook.
Oh, I've heard that one before. This way, leaves never comes back. That's okay though, because Toro's here now. What's up, Toro?
Aye.
And Christina, how was everyone's weekend? Was it relaxing after a test week?
It was very relaxing.
Very nice to hear. I'm gonna assume Toro speaks for everybody on this one because I like to think positive. And so the best way to think positive is to ignore all negative information, let confirmation bias do its work. So nice. But yeah, by the way, for the rest of the tests, we had to have test week last week because of the drop date today. So if you guys all saw your test, you can make informed decisions about that. I think everyone in the Zoom call is probably good. But yeah, for future test dates, we can talk about it. Let me know if you have like 3 tests that week. We can change because here's the secret. I don't care. I'm not attached to some test date of like, oh no, but November 5th is our day. No, I don't care, right? So yeah, you can feel free to talk about that kind of stuff. Anything else going on?
Jimmy Butler went off.
What'd you say?
Jimmy Butler went off the game last night.
I didn't see the game last night, man. I was grading tests.
Oh, sorry about that. Yeah, it was a great game.
That's awesome. That's awesome. Oh, Virginia Tech still undefeated.
I didn't watch that.
Come on, come on. We got NBA fans. We're loaded NBA fans in here, even with Safa gone. But no, but not a single Virginia Tech football fan.
I didn't even know they were playing.
Okay, no judgment, I guess. It's gonna make me hard to look you guys in the eye while I did the rest of this lecture. Anyway, yes, I'll keep you all informed. We won. I'll keep you informed every week. We did win. We beat Duke, which is important because last year Duke beat us so bad. It was like 48-10 or something like that. I was in the stands and I cried. It was terrible. It was because first of all, it's Duke. They're not good. Like, I mean, they're decent last year, but they're a basketball school that has like 2,000 people. Okay, it's embarrassing. Thank you very much, Sophos.
Yo, yeah, no, I'm hip. I'm a Redskins fan, so I'm obligated to say Daniel Jones is poop, especially because he's a Duke quarterback. I just need to put that out there real quick.
Good to know. Good to know. Yeah, no. So losing to Duke is if UVA can beat Duke, we can beat Duke. That's the point. That's the point, right? Last year we lost to UVA and Duke, so I guess that logic still kind of holds. But yeah. But this year's different. We already beat Duke with like everyone gone, and so by the time everyone comes back in December, we'll beat UVA, get that streak going again. But anyway, I can talk about this all day, and I could get upset and angry. That's no headspace to do math. Math is a beautiful, fun thing. So let's get going with some discrete math. Any requests? Okay, I'll make it up then. So we've been talking about proving things, which is awesome. We've proved a bunch of mainly like we proved a bunch of things about the rational numbers, the irrational numbers, the integers, all that. We're proving things about infinite sets now for the first time, which is exciting. We should not lose how interesting that is, that math allows us to do things with infinity that really nothing else, no other topic really does. But yeah, so today let's finish off what I wanted to do last time. And that is, oh, I should plug this in. That'll help. And that is do one last one of these closure proofs. Move on to more interesting things. Not that closure's not interesting. I wish I had some closure in my life. I still don't have closure for elementary school. I feel like I always felt like I was going to go back, but I never did. Okay, anyway. So let's look at the following claim. The claim is the irrational numbers are closed under division. Okay, so the first thing we do is we always write it formally, right? We take a claim, we write it in formal mathematics because theoretically this could be interpreted many different ways maybe, but formal mathematics is like this can only go one way. This is what this means. Everything is very, very rigorously defined. So let's get rigorous. What is the definition of saying something's closed under division? First of all, is it an existential statement or a for all statement?
For all.
Exactly, right? Because you're saying for all x and the irrational numbers, which if you can remember, we write as the real numbers. We do this like /q, because the / when we get to set theory, what that's going to mean, it's going to mean take the real numbers and take out all the rational numbers. That means like take out. So this is the real numbers taking all the rational numbers, which is exactly what the irrationals are. But for all x and the real numbers, take out the q, so all x and the rational numbers. And for all y,
Professor, a quick question.
yeah.
Why don't we use like small letter I to say irrational? Because that's what we write in math, like doing like general math.
Oh, really? You
Because
could.
that's imaginary, because that value doesn't exist. So we use a small I.
A small I like this?
Yeah.
Oh, well,
there's a difference
mean it-
between the
you mean
irrationals
that?
and
Yeah.
imaginary complex.
oh, okay. So yeah. Thank you, Alex. So these right here are imaginary numbers, and these are a different thing. The irrational numbers. So the real numbers, these are all fractions, or otherwise known as things with decimals that end or repeat. So for example, this is like 0.3s in here, or 0.56565656 is in here, or 1 is in here, or 2.375 is in here, right? That's what a rational number is. Now, a real number, which I think is what you're thinking about, like I think you're kind of getting rational and real mixed up. A real number is just anything on the number line. So just literally any point you can pick on the number line, including things like pi, the square root of 2, and -e. All those things are real numbers. So there's no imaginary numbers here. The real numbers are just all the numbers on the number line. So we're not getting any complex numbers or anything like that. The rational numbers are specifically numbers on the number line that have decimals that are nice, that either end or repeat. The irrational numbers, so the real numbers minus the rational numbers, take out the rational numbers, these are things like pi, which equals 3.14159265 something, right? Or e, which equals like 2.7, and the decimals go on forever and they don't repeat. Or the square root of 2 is the same way. So that is what a irrational number is. They're not imaginary numbers. They're just real numbers, so numbers on the regular number line that have decimals that never repeat and never end. Make sense?
Yep.
Yeah. So they're even easier in a certain sense. Yeah. Yeah. We're not going to touch imaginary numbers in this class, except for maybe me giving like a fun fact here or there and going, isn't that cool? And then I wait for a while, then like Tori will give a thumbs up in the comments, and I'll be like, nice. But anyway, yeah. So this means, just saying the irrational numbers are closed under division. This is a for all statement. This is a for all statement that says that for all x in the real and the irrational numbers, and for all y in the irrational numbers, x over y is in the irrational numbers. The point is, it's a double universal statement because it has to work for all x and y. All right, let's first do an aside. So do we think this is true or false? I think one thing that might give this hope is when we said the rational numbers weren't closed under division, right? What was our big issue? Like what was the problem child there?
Division by 0, right?
Division by 0. So I'll say note though, is 0 a rational number? Or irrational, is what I meant to say. 0 a rational number?
Wait, is 0 a rational number? Yes.
Or it's like irrational.
Okay,
Is
okay.
0 an irrational number? Yeah.
No.
No, exactly right. 0 is not in our set of irrational numbers. So that might give us a little hope. But so here's the question though. For any general irrational numbers, is x over y going to be in? What do you guys think?
No, because you could have two of the same irrational number, and that would get you one, right?
That's an excellent point. That's an excellent point, right? So you might think this makes a little bit of sense because I don't know, if x can't be written as a fraction and y can be written as a fraction, then you'd kind of think certainly x over y can't be written as a fraction because if it could be, you'd think maybe like one of them would be irrational or something. But I mean, think about this. What if you just did pi over pi? Or pick any one of your favorite irrational numbers, that just equals 1, which is very rational. So the point is, this is our counterexample. This is an example of an x and a y that are in the irrational numbers, but the division is not. So they're not closed. You can get out of the irrational numbers by dividing two irrational numbers. Make sense? Yeah, yeah. The irrationals are in an open relationship with division. So, there's gonna write the proof. And so the proof is gonna be a formal way of kind of writing what I just said. Oh, we got a chat. All right, so the proof, right? This is a counterexample proof. So this isn't, we don't have to use like direct proof or anything like that. We're not proving anything. We don't actually have to prove something about an infinite set here because we show it doesn't work. So we just define one counterexample that's a universal statement. So really this is a disproof, I should say. And so what we're gonna do here is we're gonna say disproof by counterexample. Let x equal pi and y equal pi. Note, pi is famously irrational. So x is an irrational number and y is an irrational number. All I'm saying here is that it's known that pi is an irrational number. That's another thing you can assume for this class, I guess, although theoretically someone had to prove this at some point. But it's a little bit above the scope of intro to discrete mathematics. It's also transcendental, which is another fascinating thing. Transcendental, this is a total side note here. An algebraic number is a number that is the root of some equation. So here's what I mean by that. The square root of 2 is irrational. The square root of 2 equals like 1.6, what is it? 1.8 or something like that. But it goes on forever. They just never repeat. It goes on forever, right? So the square root is irrational, but the square root of 2 is a root to this equation. Right? That's what it means to be an algebraic number. Algebraic numbers are numbers that are roots to equations like this, right? And so you can have even more complicated things. Like what if you have like x cubed minus 4, x squared plus 3x plus 5, something like that, right? All the roots to this would be an irrational number. And they could be weird. They could be things like the cube root of the square root of 2 plus 5. It could be weird things, right? Those are all algebraic numbers. Transcendental numbers are numbers that cannot be written as a root of any equation or of any polynomial like this where you have rational coefficients. And the pi is one of those. No matter what polynomial you come up with rational coefficients, you won't get pi as a root. Pi is super weird. And it's a whole thing. That's all math history. That took forever to clear. But anyway, that's not important. The point is pi is famously irrational, so x is in irrational numbers and y is in the irrational numbers. So remember, this is important right here. Right here, what we're doing is verifying that our counter example is in our domain. And we always have to do that for a counter example. Because it wouldn't be enough to come up with two numbers, right? That you divide them aren't irrational unless they actually are in the irrational numbers. We're saying things about the things in the irrational numbers. So we couldn't have like x equal 1 and y equal pi because 1 would be irrational. The point where it's verifying this is saying, we're verifying we're actually talking about the things we're talking about. So x and y are both irrational. Then x over y equals pi over pi, which equals 1, which is in Q. Therefore, x over y is not in R over Q. And that basically proves it. Thus, there is some x in R over Q and some y in R over Q mainly x equals pi and y equals pi such that x over y is not in R over Q. Therefore, there we go. Therefore, R over Q is not closed under division. Squarey thing. QED, we're done. Any questions? I think this is pretty straightforward, right? Yeah. We just in the one case it fails pi. We just and then really formally what you do is you say disprove my counterexample. You need to say that. You point out what the counterexample is. You verify the counterexample is actually in the domain you care about, and then you show that it fails the condition. And that's your proof. The point is to write formal proofs, right? They need to look something like this. So your homework 6 is going to be basically all proofs, and they all need to have this nice formal form. You say every little detail and all that kind of stuff. Cool. Well, so we've proven a lot of fun closure things here in these classes, and I think we've done enough. I think you guys get it. I'm just going to summarize what we know and what we can use in the rest of the class. So what we know is we know that Z is closed under addition and multiplication. Q is closed under the same things. R is closed under, I'm sorry. Yeah. That's all fine. Now, we also know that Q star, so Q minus the real numbers, or sorry, Q minus 0, is closed under division, and R minus 0 is closed under division. That's really all we need, and really all you can really say. We know that z is enclosed under division. We know the rationals aren't closed under division. We know the real numbers aren't closed under division because of the divided by 0 thing. And the irrational numbers aren't really closed under any of this. So, yeah. These are the things you can use going forward. These are common facts from class. Math facts. There we go. Not as famous as car facts. We good? Okay. So, now let's get into the fun stuff. This claim's gonna sound weird. But actually, let's start here. Did you guys go over like division rules in elementary school? Like little tricks to determine like if a number was even or divisible by 4 or divisible by 3 and stuff like that?
Yes. In fact, I teach this now.
Oh,
But-
there we go, Alex. So what's the division rule for 3?
So the sum of the terms is divisible by 3, and you can do this recursively.
Yeah, some of the digits, right? So here's the claim we're talking about here. And for reasons that we'll talk about in a second, I'm only going to do 4-digit numbers, but this works for everything. All 4-digit numbers n are such that n is divisible by 3 if and only if the sum of the digits of n is divisible by 3. So this might sound confusing. What this means, right, is someone give me a great 3-digit number. I'm sorry, a great
4-digit number?
any great number divisible by 3. I'm going to say, how about 135? So 135 is divisible by 3 because if you do the math, it's going to equal 3 times what? It's going to be 3 times 45, right? Because 45 times 3, 15, 3 times 4 is 12, plus 1, 135. So 135 is certainly divisible by 3. And then also notice that if you take the digits of 135 and add them together, 1 plus 3 plus 5 equals 9. And 3 also divides 9. So the claim is that n is divisible by 3 if and only if the sum of the digits of n is divisible by 3. And we can do this for anything, right? I mean, just look at 15, right? 15 is clearly divisible by 3, right? 3 times 5 equals 1 plus 5, which equals 6. 6 is divisible by 3. 21, that's going to equal 2 plus 1, which straight up equals 3, clearly divisible by 3. This always works. It's kind of weird, right? So, before we start talking about that, let's list one fact that we're going to need. And this is a fact that you're going to prove in the homework to show up this proof. And here's the fact. I'll just write it mathematically. For all A and Z, for all B and Z, and for all C and Z, A divide B and A divides C implies A divides B plus C. is a fact. All we're saying here, all this means is if A divides B and A divides C, then A will divide B plus C. And just do some examples of that to show it doesn't make sense. If A was like 5, for example, note 5 divides 10, and 5 divides 35. And then clearly 5 also divides 10 plus 35, which equals 45. If it divides both, it'll divide the sum. Right, like 7 divides 21, and 7 divides 28, and then 7 will divide 21 plus 28, which equals 49. These are examples. These don't prove it works. We prove it works in the homework. But the point is, I think this is easy enough to think about. Like if 7 evenly goes into 21 and 7 evenly goes into 28, you would think it would kind of evenly go into like 21 with 28 stacked on, right? That makes sense to me. And hopefully it makes sense to you by Friday. So any questions on what this means? Cool.
Just a quick clarification. So we can use this as like a given fact, or do we have to prove this
Um,
as part of the proof for the homework?
the homework is going to be exactly to prove this.
Oh, okay, cool.
Yeah. But for now, we're going to use it as a fact. Just because we don't have time to prove everything in class, sadly. I want to do some more interesting things. So yeah. So this is what we proved in homework, but for now we can use it as a nice red fact. So what's the first thing we do when proving anything?
Formally stated.
Formalize it, right? Let's write it formally and really be clear on what we're talking about here. So formally, this is going to be a little weird because A is divisible by 3. That's easy enough, right? That just means 3 divides n. But if only if the sum of the digits of n is divisible by 3, that's a little weird to formalize. And let's notice this, right? You take any 4-digit number. So for example, if you take 2020, what a year. What's 2020 saying? Like if we go back to elementary school, right? We're talking about like what our number system actually means. What's 2020? Like what's this 0 refer to?
0 ones.
Yeah. This means we have 0 ones. This 2 here means we have 2
tens.
The 0 here means we have 0 100s or 10 squares. And this 2 here means we have 2 thousands or 10 cubes. So 2000 equals 0 times 1 plus 2 times 10 plus 0 times 10 squared plus 2 times 10 cubed.
Well, if you're going to write it that way, you maybe should write it as 10 to the 0 and 10 to the 1.
Not that way to look at it. Yeah. So, just to give you another example, 1967. I don't know why. I have no idea what happened that year. But that would be 7 ones, so 7 times 10 to the 0, plus 6 tens, plus 9 hundreds, plus 1 thousands. So boys, this is what digits really mean. It can be written this way. So the first thing I'll do is I'm just going to define a set here. I should do it in blue for some reason. Let's define a set S, which is the set of 4-digit numbers. So let's define S to be the set of all numbers that can be written like this. A0 times 10 to the 0 plus A1 times 10 to the 1 plus A2 times 10 squared plus A3 times 10 cubed, such that they're mowing the lawn very loudly in my apartment complex, apparently. Good timing. such that A1, A2, and A3, what are the restrictions on the digits?
They have to be real numbers.
Have to be real
Natural
numbers?
less than
What?
10. Natural
Yeah.
numbers less than 10. Greater
Exactly. They have to be
Yeah.
specifically
Oh yeah.
0, 1, 2, 3, out to 9. Because you can't have like, the way we define our number system at least, you can't have like the square root of 2 pi, the square root of 2 pi 0e or something like that. You know what I mean? Or even like 1.2 or something. You need whole numbers, specifically less than 9. Any questions on this definition right here? And by the way, this is going to be the exact same thing as all the numbers between 0 and 1,000, or sorry, 0 and 10,000 or 9,999. But it's better for us to look at it this way for our proof. So these are all the 4-digit numbers. Because they're all the possible numbers that could be written like this, where you have 4 digits. Where the digits are A0, A1, A2, and A3.
Small comment is that should we, like, I don't think it actually in practice matters for the negative 4-digit numbers, but should we make some mention for negatives in our proof?
Yeah.
Or
No, we're just gonna forget about those for a second. But this idea is gonna work for everything. And so if you wanted to extend it, you totally could. But for simplicity's sake, we're just gonna keep it like this for now. Good. I mean, you would need to make all of these negative. But so it would be between 0, -1, -2, as -9 for all of these. That would work. But yeah, so you're saying, let's just not worry about that for now. So that was good. So first things first, let's write a formula, right? And formally, the way you can write all 4-digit numbers n are such that n is divisible by 3 if and only if the sum of the digits of n is divisible by 3. Formally what you're doing there, you're saying that for all 4-digit n, and s is exactly defined as all the 4-digit numbers. So you're saying for all n and s, so we got this taken care of. N is divisible by 3, so 3 divides n. If and only if, what's if and only if?
Biconditional.
Biconditional, perfect order, so it goes both directions. If and only if there exists A0, A1, A2, A3, and 0, 1 to 9, and this set of whole numbers here, such that n equals A0 times 10 to the 0 plus A1 times 10 to the 1 plus A2 times 10 squared plus A3 times 10 cubed, where this happens, and 3 divides the sum of the digits. So all this right side is saying is that if you take like kind of the 4-digit number expansion or the 4-digit number way to write n, which you know you can do because n's in s, so this has to exist. If you take that, 3 will divide the sum of the digits. So this is the full way of saying this. So if we can prove this, we do prove what we're saying here, our division rule, that you can tell the number is divisible by 3 simply by just adding the digits together and seeing it's divisible by 3. For a 4-digit number at least, but you'll see this works for everything. So any questions on what we're doing here? Good, okay. So let's do it. First things first, and that is to notice that we're proving a biconditional. And so I'll say note to prove, note P of X if and only if Q of X, which is what we have here is a biconditional. This is equivalent to P of X implies Q of X, and P of X, and I'll put the arrow going this way. P of X implies Q of X, and Q of X goes to P of X. So the point is to prove, and these are two separate statements. Right? We've talked about this a lot, how the converse is a different statement from the original. They're two just separate statements. So in order to prove a biconditional like this, so to prove that P of X if and only if Q of X, we need to prove P of X goes to Q of X first. And separately, we need to prove that Q of X goes to P of X. So I'll say to prove biconditionals. That's just happening here. So this is how we prove all biconditionals. Whenever we prove a biconditional, we have to prove both directions separately. So it's a little harder because it's kind of two proofs here. One going from P of X to Q, one going from Q to P. But it's all fun. More math than never hurt anybody. All right. So let's do our aside and figure out why we even think this is true to begin with. So let's first talk about, let's first talk about this direction right here. So this direction, right, is we're going from n divisible by 3 to 3 divides the sum of the digits. So assume 3 divides n. Why would 3 divide the sum of the digits? Let's do an example, right? For example, 3 divides 3,135 for sure, right? Because 3,135 is going to be 3 times 1,045. There's the effect. So let's think about this, right? 3,135. If you write it out as our 4-digit decimal expansion thing, this is 3 times 10 cubed plus 1 times 10 squared plus 3 times 10 to the 1 plus 5 times 10 to the 0, which is just 1. So I'm just going to write like 5. And maybe you better look at it this way. This equals 3 times 1,000 plus 1 times 100, which is just 100, plus 3 times 10 plus 5. So we know that 3 divides this sum right here because it just equals 3,135. So 3 divides this. We want to show, use WTS for want to show. We want to show that 3 divides 3 plus 1 plus 3 plus 5, since this is the sum of our digits. So the question is, how can we go from 3 divides this to 3 divides that?
So the way I've always thought about it is you can take out factors of 3 are multiples of 3, rather, sorry. And if you're taking it out of 1,000, the closest multiple of 3 that's probably useful to think about is 999, which will give you a remainder of 1 for every 1,000. And a similar argument could be made for 100 with the multiple 99, right? 3 times 33, which will give you 1 for every 100. 9 and 10 would give you 1 for every 10, right? So you would basically have these numbers fall out, right, with 3, 1, 3, 5.
This is a brilliant idea. Here's what Alex is saying. He's saying that this, like saying 3 divides this, I mean, this really equals 3. 1,000 is 999 plus 1. 100 is 99 plus 1. 10 is 9 plus 1. And we still have just 5 left over. The point being, we can write this as, it doesn't really matter what the digits are here. 3 happens to be divisible by 3, but what if it started with 4, whatever it was? It doesn't really matter what that first digit is, because now we can kind of distribute it out like this. And here's the key. Once we have it like this, we can group. Notice what falls out. The sum of the digits falls out. Because at each step along the way, for each one of our digits in here, right, we always wrote it, we always were able to get like a 1 out of here. This is 999 plus 1, so you distribute, you get that digit back. This is 99 plus 1, distribute, you get the digit back. 9 plus 1, distribute, you get the digit back. So this equals 3 times 999 plus 99 plus 3 times 9. So I grouped this together. Plus, what's left over? Oh, sorry. What's left over is this, and this, and this. So plus 3 plus 1 plus 3 plus 5. And here's the thing to notice. Three divides that. Because 3 divides 999, 3 divides 99, and 3 divides 9, 3 will always divide this. And also notice that 3 divided this thing up top. 3 divides this big number, which equals this whole thing, and 3 divides this part of the number. So by our fact, if A divides B, A divides C, then A divides B plus C, A must divide this number here. We're going to prove it formally, but is that starting to make sense to people, or is this just all over the place? I'll do one more kind of example, then we'll get to the proof. So another example would be, let's do a simpler one. Like let's do a small digit one. 3 divides 28, right? And 28.
Wait, what? Are you sure?
Nope, you're right. Sorry, 27. Good call. 3 divides 27. And thank you for that. That would have been all. I proved that that'd be a problem. 3 divides 27. And 27, right, equals 2 times 10 plus 7. Which equals 2 times 9 plus 1 plus 7. Which equals 2 times 9 plus 2 plus 7. notice here, we've gotten the sum of the digits because we always had a +1, so each digit kind of came out individually. So here's the sum of the digits. This is the thing that we want to prove is divisible by 3. So we have 3 divides 27. We want to prove 3 divides this. Well, notice that's 2 times 9. 3 divides this, right? 3 divides 27. And 3 divides 2.9, or sorry, 2 times 9. So 3 must divide 27 minus 2 times 9. And what's 27 minus 2 times 9? If we subtract 2 times 9 from both sides here, right, we get 27 minus 2 times 9 is going to equal 2 plus 7. And this idea will work for any number. Does this make sense? Okay, well, let's get going. Let's actually start to prove it. So the point is, yeah, that's just the point. The point is we're going to take our number that we know is divisible by 3, and we're going to write it in a way that we're going to have something divisible by 3, something divisible by 3 plus the sum of the digits. And if you can do that, well then, if you subtract, you have something divisible by 3 minus something divisible by 3, which has to be divisible by 3 by our fact. And what's left over is the sum of the digits. So the sum of the digits must be divisible by 3. All right. This is the proof. And the proof is going to be done. That's his proof right there. And the proof is going to be done in a couple of stages. The first stage, go in the first direction. So the first direction, right, we're starting from here and going to here. So I'll say, like any direct proof we do, right, let n be a particular but arbitrary element of S, right, because they all come from S, with three divides n. So we're assuming n meets our conditions. Just assume we have any old n, any particular arbitrary n, there's a and S, and you get 3 divides n. That's how all of our direct proofs start. Then, note, since n is in S, by definition of S, because S is all these numbers here that can be written like this, there exists an A0, A1, A2, A3, in 0 to 9, such that n equals A3 times 10 cubed plus A2 times 10 squared plus A1 times 10 to the 1 plus A0. That's just by definition of being an S. We haven't done anything special yet. All right. Note, here's where the special part comes in. N equals A3 times 10 cubed plus A squared times 10 squared plus A1 times 10 to the 1 plus A0. This is by substitution, which equals A3 times 1,000 plus A2 times 100 plus A1 times 10 plus A0 by evaluation, or is evaluating what 10 cubed and 10 squared and all that means. And this equals 999 plus 1. 100 equals 99 plus 1. And 10 equals 9 plus 1. Right? And all this is by observation. Just observe, each one of these, 1,000, 110, are all going to be one of these 999 things plus 1. 99 plus 1, 9 plus 1. They're all going to be like that. The important thing is they're one more than a multiple of 3. Now, if we write this out, this is going to be A3 times 999 plus A3 plus A2 times 99 plus A2 plus A1 times 9 plus A1 plus A0 by distribution. And what's this equal? This is going to equal, I'm going to group them in this way, 999 times A3. This is because multiplication is commutative, and it looks weird to me to have a variable in front of a number. We normally put numbers in front of variables. Doesn't matter. 999 A3 plus 99 times A2 plus 9 times A1. Right, if we group these three together, then what's left over is A3 plus A2 plus A1 plus A0. And this associativity is by associativity. Just meaning that we can rearrange this however we want. So far, all we've done is we've just said because n is in S, it can be written like this, and being written like this, if we just kind of rearrange some stuff using pretty basic algebra, we get to this. And I don't want to erase this, so we're going to continue with pen and paper. All right. So, right, if we keep going, right, we know it can be written like this. Then, note, it's actually like a marker. Maybe a better pen. There we go. Note, 999 A3 plus 99 A2 plus 9 A1. This right here this equals 3 times 333a3 plus 33a2 plus 3a1. Right? Just write it out. Thus, 3 divides 99983 plus 9982 plus 9a1. Right? Which makes sense, right? I'm saying it right a lot. Then, since 3 divides in and 3 divides are 9983 plus 99a2 plus 9a1 by our red fact above, right? By that fact above, 3 must divide in minus 99a3 plus 99a2 plus 9a1. But timeout. What's n? N equals this. N equals 999a3 plus 99a2 plus 9a1 plus these guys. That's n. So n minus this we'll have that right there. These two cancel. So this equals a3 plus a2 plus a1 plus a0. Hence, 3 divides a3 plus a2 plus a1 plus a0, meaning 3 divides the digits of n. Actually, we're not squared yet. We're done with the first part. Now, here's the thing. Even if our aside conversation didn't make a ton of sense, that was confusing, I hope that every step I made here along the way made perfect sense. And if every step I made along the way made perfect sense and it leads to this conclusion, that means this conclusion must be right, right? Because like if you have a valid argument with true premises, then you have a true conclusion. So, on that vein, does anyone have any questions about this? Seriously, try to point out, is there anywhere in this chain of reasoning that you're not sure about? Or that doesn't make sense to you?
There was something that bothered me a little bit, and I think it's fine, but it's like the by the red fact above, but you can, it would be better to rewrite it as 3 divides n plus negative of
Oh, you're right. You're right.
1 and so on.
What I'll say
but
then
like,
is, to save my proof, I'll change this fact to b minus c, which is also true. And this is true because if a divides c, then a will divide minus c. But yeah, but you'll see why that's true when you prove it on the homework. It's not hard.
I mean, no, like I still agree, but that's
Yeah,
just
no, you're
a
right there. You're right there. That's a
nitpick.
little bit. But anyway, but anyone else, right? So we just started out by assuming ends and s with 3 divides n. So we just assume that we're in our domain and we have the predicate. And we're trying to prove the conclusion. And, well, by definition, we have the first part. By definition, there exists these numbers, since you're in S, there exists these numbers that work this way. So you get A1, you get A0, A1, A2, A3 that equal n, right? Like that. That's just by definition, that's fine. But then we can rewrite that as this whole thing. And then we notice that this part is divisible by 3 because we can literally write it as 3 times, and then we can write down what that is, right? And then we have 3 divides n, and 3 divides this part. So 3 will divide n minus this part by our fat, meaning it has to divide this part, which happens to be the sum. The sum of the digits happens to pop out if we write it correctly. This is kind of brilliant, right? I think maybe a lot of this felt like we were kind of trudging through some algebra, right? But if we take a step back and look at it, this is kind of brilliant. We were able to prove that if 3 divides n, and 3 is a 4-digit number, or n is a 4-digit number, then you're going to get that 3 divides the sum of the digits just simply by rewriting n in a super clever way. This happens all the time in math, where math most of the time, the way things are actually proved is by just simply changing your perspective, right? So instead of looking at n as this, as a 4-digit number like we typically do, look at it like this. And if you look at it in this changed perspective, it's very clear then that 3 will divide this, because 3 divides this, and 3 divides this, so 3 will divide this minus this, which is this. I've said that before. The point is, just changing our perspective here made it obvious. And so really the only thing we had to do is prove that our perspective change didn't change the meaning, which it doesn't, because they're just equal. Any questions? I have a question. Are we done with the proof?
No, we still have to go the other way.
Yeah, we have to prove the other biconditional.
Yeah, so next time we'll do that, where we still have to prove this way next time. And so that means if you start here, if you start with this assumption that you can write in this way, and 3 would divide A0 plus A1 plus A2 plus A3, then prove 3 divides n. It's going to be just as easy. It's basically just going to be reversing what we already did. But we have to prove it. And that is class. So, I hope that the takeaway from this class is that I want to show you guys something a little more complicated. I hope I didn't overstep my bounds. Just to kind of show you guys that this proof thing, it's more than just, like, even when we know right now, it's more than just proving that, like, an even plus an even's an even, right? We can do that. Right, but it's more than that. We can actually prove some pretty interesting, non-obvious stuff here. Like, you might have heard this rule in elementary school. You can do this division rule, right? But unless you teach it like Alex, you probably never knew where it came from. And most people might know this exists. Often might know this exists, but never, ever, ever question or know why it works. Like, how would you prove it about everything? That's how you prove it. The one caveat here, and that'll be class. That's class. That's class. Thank you, everybody. I'm gonna stop recording.